Hi, this is Dr. Bay and here's Bugsy, and today we'll be learning about molecular representations of organic molecules. We'll delve into how to draw bond line structures and an introduction to functional groups. Stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
There are a bunch of different ways that chemists use to draw molecules. Let's take a look at the structure of isopropanol, which essentially is rubbing alcohol often used in disinfecting wipes. So the molecular formula of isopropanol is C3H8O, but we don't want to draw 8 hydrogen atoms in a row. So what we can do is we can rewrite the molecular formula as a condensed structure to show that isopropanol consists of 2 methyl groups in addition to an alcohol group. In this way, bonds are not drawn, but rather groups of atoms are just clustered together. You previously learned about Lewis structures where we can show all of a molecule's bonds and lone pair of electrons as shown here. You can see that 2 of the lone pairs of electrons on oxygen are drawn in order to depict a full valence. Another way to draw isopropanol without showing every single carbon-hydrogen bond is to draw what's called a partially condensed structure. But you can imagine that if you had to draw the structure of an even larger molecule, these methods could take forever, and that just isn't an efficient use of our time. Molecular formulas don't often provide enough information, Lewis structures take way too long to draw, and condensed drawings are only suitable for relatively simple molecules like isopropanol. So today, we're going to learn the rules for drawing what's called a bond line structure, which is a much simpler way to draw organic molecules. Bond line structures are drawn in a zigzag format, where each corner or vertex represents a carbon atom. Take this molecule on the left, for example. The molecule has 6 carbon atoms, which means when we draw its bond line structure, we're going to draw a zigzag line with 6 vertices or endpoints. Note that even the ends of a zigzag line are also carbon atoms. Furthermore, double bonds contain sp2 hybridized carbon atoms and are still drawn in a zigzag format, but triple bonds, because they contain sp hybridized carbon atoms, are drawn linearly. Notice that no hydrogen atoms are drawn in a bond line structure. Rather, it is assumed that each carbon atom that is neutral is bonded to enough hydrogen atoms in order to complete its octet of having a total of 4 bonds. Secondly, when drawing double bonds, we want to make sure to draw all of the bonds as far as possible. And thirdly, all heteroatoms like nitrogen, oxygen, or any halogen must be drawn. Also, any hydrogens attached to a heteroatom also should be drawn. And fourthly, never draw a carbon atom with more than 4 bonds. That is a no-no, and definitely you'll get points taken off for that. Now that you've learned how to draw bond line structures, I'd just like to introduce the topic of constitutional isomers. These are compounds that have the same molecular formula but have a different connectivity of atoms. In order to be constitutional isomers, at least one bond had to break and reconnect at a different atom. Take this example of C4H10. On the left, we have butane, where all 4 carbon atoms are drawn in a zigzag format. But if we break off the last carbon on the right with its 3 hydrogens and reattach it, we can redraw this molecule as 2-methylpropane. However, if we count the number of carbons and hydrogens in each of these 2 molecules, they both contain 4 carbons and 10 hydrogens, but they only differ in connectivity, which means that these 2 compounds indeed are constitutional isomers. As we mentioned previously, all heteroatoms and their corresponding hydrogens must be drawn even in bond line structures. Different heteroatoms make what are called functional groups, which give a molecule a set of physical and chemical properties. Functional groups are important because they are 1. The units by which we divide organic compounds into classes, 2. They are oftentimes the sites of chemical reactivity, and 3. They're the basis for naming organic compounds. Now let's take a deeper dive into a few important functional groups that you will encounter during your course. An alcohol is a compound that contains a hydroxyl group, also known as an OH group. For example, if we take apart the name of the molecule ethanol, we find that eth is due to the fact that the molecule contains 2 carbons, and an or an is because all of the bonds are single bonds, and it has the ending ol because it contains an alcohol group. Alcohols are classified as primary, secondary, or tertiary, depending on the number of carbons bonded to that carbon bearing the OH group. Amines are another functional group, which is when a molecule contains an amino group. Amines, like alcohols, can also be primary, secondary, or tertiary, depending on how many hydrogens are directly attached to the nitrogen atom. 5 functional groups fall under the category of all containing carbonyls, or C double bonded to O. Aldehydes are a carbonyl bonded to a hydrogen atom. Ketones are carbonyls bonded to 2 carbon atoms. Carboxylic acids are a carbonyl bonded to a hydroxyl group. Esters are carbonyls bonded to an oxygen and a carbon. And amides are carbonyls bonded to an amine. Here's a comprehensive table of functional groups that you'll come across during this course. Feel free to take a screenshot and print it out so you'll have a reference sheet during the rest of this class.
Organic.